So, we had earlier discussed the reactor performance equations for 3 different types of reactors that are used for carrying out the enzyme catalyzed reactions, that is batch, plug flow reactor and continuous stir tank reactor. Now, while the choice of the batch reactor is primarily based on many factors other than the reactor performance, mainly on the basis of the additional requirement of the reaction. For example, if you require a very stringent pH control or a temperature control or addition of a substrate, addition of a secondary substrate at a different speed, at a different period other than the beginning of the reaction, then batch reactor provides you some convenient operational convenience. Rather, I would say yes, the better term would be the use of batch reactor is based on certain operational conveniences, but based on the reactor performance the choice remains between use of a CSTR and a PFR. And here I have given a summary of the reactor performance equations for CSTR and PFR under 3 different kinetic regimes. The first line indicates the reactor performance with respect to Michaelis-Menten kinetics, and the second and the third, the second line refers to when the reactor performance is in the 0 order regime, that means when substrate concentration is much higher than the Km value, and the third line is in the first order regime when the substrate concentration is less than the Km value. Now, of course, when we say higher or less than the Km value, when we compare substrate concentration with the Km value, what we essentially are looking at in the case of a 0 order regime, we often look at that the Km value K dash m is less than usually 0.01 S naught. That means substrate concentration is almost 100-fold or more than the Km value. Similarly, in the case of first order regime, it is again the same thing, that the K dash m is usually greater than say 10 S naught, 10-fold increase usually gives you a reasonable performance towards the first order regime. And as you notice that in the case of 0 order regime, the reactor performance is identical in both the cases in CSTR and plug flow reactor, excepting that the magnitude of tau is altered by epsilon, that is the voidage. Otherwise, the reactor performance in the 0 order regime is identical. On the other hand, in the case of first order regime, the performance of PFR, if you look at from the point of view of fractional conversion, the effect of fractional conversion on the quantity of enzyme required and on the quantity of or the value of the space time. I think to be able to compare the reactor performance, I think what we need is to look at 2 different things, the fractional conversion and the quantity of enzyme required. Now, these 2 parameters can be looked at from this these expressions. We had also looked at yesterday the relative quantity of enzyme required in CSTR to PFR is given by this ratio, and here as you will notice that as we increase the fractional conversion, the relative quantity of enzyme required for a first order regime significantly increases in the case of CSTR. In the 0 order regime there is no difference. So, therefore, when we shift from 0 order to first order regime, the efficiency of plug flow reactor improves in terms of its enzyme requirement, or of course, even in terms of your space time. If for example, there are 2 parameters, either you can keep the space time constant and increase the enzyme loading, or you can keep the enzyme loading constant, then you can the space time can be varied, and in the case of PFR the space time required will be much less compared to in the case of PFR compared to CSTR in the first order regime. And then of course, the 0 order regime the space time will also be identical in the 2 cases. Of course, the intermediate regime is that of the where Km and S0 are of the comparable value, that means let us say between 1 and 10, that means say S0 is something like about 5 km values. In that case, the performance will be dependent on the magnitude, not only fractional conversion, but also on the magnitude of km value. As the relation between S0 and km, the performance will be dictated, and it will. Now, just to give you a bit of quantitative picture under 3 distinct conditions, here I have taken 3 different fractional conversions, 0.8, 0.9 and 0.99. Of course, I think I must also state here that ideally for most of the enzyme catalyzed reactions, we will try to aim at the fractional conversions as high as possible. Of course, 100% is the perfect, but very often you may not be able to touch that, and one may like to have fractional conversion anywhere between 0.9 and 0.99. I mean, that is usually the pattern if the reaction is irreversible, practically irreversible. So, under those conditions and assuming S0 is equal to 1 molar and epsilon of 0.5, now the E relative in the case of a first order enzyme at 0.8 is 1.24. Let they are any arbitrary unit, do not bother about units, but these are the relative ratio. So, the 1.24, as soon as you go to 0.9 conversion, the relative quantity of enzyme required is 1.95, almost about 1.5 times. But when you go from 0.9 to 0.99, you see the relative quantity of enzyme becomes more than 5 times, and it very significantly increases the relative quantity in the first order enzyme. And if you consider from 0.8 to 0.99, the ratio is still higher, and the relative quantity, and the same relationship will also hold good for space time, the tau. If you keep the enzyme quantity constant, if the enzyme loading is constant, then the tau will also have the similar ratio, because as you will notice that in our reactor performance equation, the left hand side is K2 E0 tau equal to so and so, and so therefore both are have the same relationship as far as the fractional conversion is concerned. In the case of 0 order enzyme, there is no complication. Whatever is the fractional conversion, the relative quantity required are identical, the same space time. On the other hand, again in the case of Michaelis-Menten kinetics, when the EM and S0 are comparable, again it will vary, and it will be a function of Km. What is the magnitude of Km in comparison to substrate concentration? Here we have chosen 1 molar here. So, this is what is the point, and as a matter of fact, there is another point besides the fractional conversion, the enzyme quantity required and the space time required. There is another important parameter of reactor design, which you will recall when we defined the parameters, we talked about productivity, the reactor productivity. That is your PR, and we are defined at x S0 upon tau. Now, essentially you will notice that the reactor productivity also is linked with the fractional conversion. In the case of the 2 types of reactor, the reactor productivity is directly linked with the fractional conversion, and obviously as it is also linked with the tau, inversely proportional to tau. If the tau increases, the productivity goes down, and therefore the fractional conversion, again whatever we have discussed about relative quantity of enzyme or the space time as a function of fractional conversion, a reverse phenomena or the reverse behavior is true for productivity. Now, when you increase fractional conversion, the productivity will go down, and productivity and for the first order design, the productivity of PFR will be much higher than the CSTR. Now, I was just trying to relate productivity and the quantity of enzyme or the space time. The quantity of enzyme required and the space time are almost analogous parameters. I mean, their behavior on the basis of the fractional conversion required is identical, but the effect of the fractional conversion on reactor productivity is just reverse, because tau appears on the denominator x S0 upon tau. So, if the tau decreases more significantly with fractional conversion, the productivity will increase more significantly, and therefore in the case of first order enzyme, the productivity as a function of fractional conversion increases much more faster in the case of PFR than CSTR. the quantity of enzyme required or the quantity of or the value of tau increases more in the case of CSTR with increasing fractional conversion, but the productivity increases more drastically, very significantly in the case of PFR when fractional conversion is increased. But in general, with the increase in fractional conversion, the productivity will go down in both the cases. In both the cases, because you will see the reactor performance equation, because the decrease in the decrease in tau will be much faster compared to increase in fractional conversion. And so, in general there will be a decline in productivity as the fractional conversion increases as a general, but the relative decrease will be more pronounced in the case of CSTR than in PFR.
So, relative decrease or increase of tau?
Not tau, productivity, relative decrease of productivity.
So, the effect of tau is more pronounced on productivity.
Yeah, effect of tau, no, the tau and productivity are related inversely. The tau and productivity are inversely related, and therefore, if the tau increases with increase in fractional conversion more pronouncedly in the case of CSTR, the reverse will happen in the case of productivity. And so, therefore, I think one should very clearly understand the relationship between fractional conversion, enzyme quantity required or space time and productivity. And very often the choice of the right type of reactor, whether to use a CSTR or a PFR, is dependent upon the type of reaction or type of the reaction system we are looking at. For example, in case we are talking of a very high value product, say for example steroid transformations, a pharmaceutical product where the cost of product or the cost of substrate is very high, you do not want to waste the substrate, then case we will like a very high fractional conversion, because we will not like any substrate to be remaining unconverted, because the cost of substrate is very high, and in that case even at the cost of productivity, because if you go for higher fractional conversion the productivity will decrease, but even that is desirable to have a higher fractional conversion at a lower productivity. On the other hand, if you are talking of a lower or reasonable value product, or in those cases where the even unconverted substrate can be used along with the product, you do not have to separate the product for application, and as is the case in the case of glucose fructose syrup, when you isomerize glucose to fructose, essentially the final product is a mixture of glucose and fructose. We never attempt to get the reaction converted to completion, because then the time of residence time required, the space time required in the reactor will be very high, because it is a reversible reaction, and therefore the final reaction product usually a mixture of glucose and fructose, where fractional conversion is only 0.4 or 0.45, not even 0.8. But the advantage is that the ultimate mixture of glucose and fructose is used as a product, no separation is attempted. So, in those cases lower fractional conversion, but we keep a very high stake on productivity. Productivity is tried to be maximized, so that and of course the cost of product is not very high, so productivity becomes a very important parameter. But if the cost of product is very high, which also requires to be separated from unconverted substrate, then it is desirable to have a high fractional conversion even at the cost of productivity. So, I think we must clearly understand the interrelationship between the kinetic order regime, the fractional conversion and the productivity. Another parameter which is very important in the case of reactor performance is the effect of substrate and product inhibition. Now, many enzymes, most of the enzymes rather I will say, most of the enzymes, enzyme catalyzed reactions will experience some kind of inhibition. Well, of course, one inhibition, as we talked, that you can add a third component in addition to substrate and product and add another inhibitor for either for any purpose, for a study or anything usually, but that does not come into picture when we talk of industrial reactions using enzymes, because we will not like to add an inhibitor to the system for carrying out an enzyme catalyzed reaction for commercial purposes. But even we do not add, but still most of the enzyme catalyzed reactions are inhibited naturally by either substrate or the product. Of course, product is a very common case, the inhibition by product is a very general feature for all enzyme catalyzed reaction, but some enzyme reactions are also inhibited by substrate, and this effect, because the concentration profile of substrate and product in the two cases of PFR and CSTR are different. For example, in the case of CSTR, the concentration of substrate in the reaction mixture is very low, same as in the outlet, or another way the concentration of product is very high in the reaction mixture. So, if a system, let us say, experiences product inhibition and you use a CSTR, you are making the reaction going at a very high product concentration in a very, and that means in extremely inhibited conditions, reaction rate can be very slow. On the other hand, the reverse might be true in the case of plug flow reactor, and so basically the incorporation of effect of substrate and product inhibition on the reactor performance equation becomes very important. And of course, while we are considering the all other conditions of the isothermal operation or partitioning effect, diffusional limitations are still valid, we are still talking about idealized reactors, we are only changing the kinetic part. That means, if we consider, and if we let us take a general case of substrate inhibition where the reaction rate is given by K2 E naught upon 1 plus K dash m upon S plus S upon Ks. Now, general, I mean, kind of a expression. Now, this is the Ks is the substrate inhibition constant, dissociation constant, and Km the natural, I mean, Km value for the reaction. If you recall, I mean, we discussed the substrate inhibition kinetics, in which the excess of substrate causes causes binding of two substrate molecule to the enzyme molecule, and which becomes a dead end complex. So, under that condition, if you look at in the case of CSTR, and you can develop the reactor performance equation for such system also on the same lines as we did for Michaelis-Menten kinetics. That means, you make a mass balance across the reactor, simplify it, and the final reactor performance equation for these cases for CSTR is x S naught plus K dash m x upon 1 minus x plus S naught square upon Ks x minus x naught, sorry, x minus x square equal to K2 E naught into tau. In the case of PFR, the same expression, the same reaction expression, reaction rate expression will result in x S naught minus K dash m ln 1 minus x plus S naught square upon 2 Ks 2 x minus x square equal to K2 E naught epsilon into tau. So, now you end up in the reaction performance equation gets modified, and as you will notice that in the case of substrate inhibition, the performance of CSTR will be far superior. I mean, you can just use these two equations and substitute the values of, let us say, arbitrary values for fractional conversion at a given substrate concentration. The performance of CSTR works out to be far superior compared to a plug flow reactor, because the concentration of substrate at any given time, I mean, physically is much lower than in the case of PFR, which for a bulk part, more than half of the part substrate concentration is very high, only in the upper half the substrate concentration goes down, and the reaction rate, in fact the reaction rate varies in the PFR along the length of the reactor. If you look at product inhibition, now again product inhibition also can sort of have influence in two modes, either the product can inhibit competitively or non-competitively. Of course, uncompetitive cases are rare, as I mentioned earlier also. In most cases the inhibition patterns are usually either competitive or non-competitive, and the case of product inhibition, the reactor performance, the reaction rate is given by K2 E naught upon 1 plus K dash m upon S 1 plus P upon K dash P. Now, this K dash P essentially is the inhibition constant, which is a competitive inhibitor of the reaction. Now, in this case also one can write down the reactor performance equation for CSTR as S naught x plus k dash m x upon 1 minus x plus k dash m upon k p S 0 x square upon 1 minus x equals to k 2 E naught tau. In the case of plug flow reactor, the reactor expression will be S 0 x into 1 minus k dash m upon k p minus k dash m ln 1 minus x 1 plus S naught upon k p equals k 2 E naught tau into epsilon. So, again in the case of product inhibition in the competitive mode, I mean in general, as I mentioned, in the case of product inhibition, the PFR will have a more superior I mean as I mentioned that even in the case of a uninhibited reaction, the performance of PFR, the relative performance of PFR as the fractional conversion increases is superior, but if in the case of reactions that undergo product inhibition, the performance still becomes more superior, that is the relative quantity of enzyme required or the relative quantity the relative value of the space time required in PFR for increased fractional conversion is much higher in the case of CSTR compared to PFR. On the other hand, the analogous relations in the case of non competitive product inhibition, where the reaction rate can be given by k 2 E naught upon 1 plus k dash m upon s 1 plus p upon k dash p. The CSTR reactor performance comes out at x s naught plus k dash m x upon 1 minus x plus k dash m upon k p or other k dash p into 1 minus x upon s 0 x square plus x square s 0 square upon k dash p, and that is equal to k 2 E 0 tau. In the case of PFR, the expression is arrived as x x 0 1 minus k dash m upon k dash p minus k dash m ln 1 minus x 1 plus s 0 upon k dash p plus s 0 square x square upon 2 k dash p equal to k 2 dash E 0 tau into epsilon. Now, so basically when the enzyme is subjected to inhibition by excess substrate, it is more serious in the case of a plug flow reactor. As I mentioned, in the case of substrate inhibition, as I mentioned that if the enzyme is subjected to substrate inhibition, is more serious in the case of PFR. The inhibition effect of inhibition on the reactor performance is more detrimental in the case of PFR, but I mean it can be sort of kind of improved, our situation can be slightly improved if you make say intermittent feeding of the, like for example, if you use a plug flow reactor in which the feeding is done at more than one point. That means you introduce the substrate you do not use a high substrate concentration right at the beginning, but you make a I mean those kind of modifications can always be looked at. And of course, on the other hand, the effect of product inhibition is more serious when particularly when high conversions are required. Now, it is not only the effect of product inhibition is more serious in the case of a CSTR compared to PFR, but when high substrate when high fractional conversions are required, the product inhibition becomes still more serious. In the you see the product inhibition is more detrimental in CSTR compared to PFR, because the concentration of product at which the reaction is undergoing is much higher in the case of CSTR. But when higher fractional conversions are required, the problem becomes more and more serious, because the product concentration will be then high when the fractional conversion desired is high, and therefore, in those cases almost plug flow reactors become almost a necessity if high fractional conversions are required, because in the case of CSTR if the fractional conversion required is not very high, then of course one can tolerate the conversion the effect of the product inhibition, but if high fractional conversions are required, which is usually the case, the PFR becomes, and that is one of the reasons why you will notice in the whole literature that a large number of immobilized enzyme systems have been reported to be used in a plug flow mode, in a packed bed reactor mode rather than a CSTR mode. Of course, unless you require there is a requirement of pH control, or of course in some cases I mean if you want to add certain let us say another constituent at a later stage. Now, another of course these are the standard kind of inhibition patterns which we are familiar with, substrate inhibition or a product inhibited which is a non competitive or competitive. I do not consider it necessary that a third inhibitor to be added. It can be either substrate or product which can cause inhibition and which has to be taken into account while making a reactor design or while analyzing the reactor performance in the case. Now, another situation arrives which is much more complex, that many practical situations, of course these are theoretical situations which are comparatively simpler. In many practical situations the inhibition patterns are usually complex, they are not as simple. For example, just one of the example which I have illustrated here, the hydrolysis of penicillin to 6-AP and phenylacetic acid by penicillin acylase, an enzyme catalyzed reaction which is used commercially all over the world, and particularly 6-aminopenicillic acid is used as an intermediate for synthesis of ampicillin. And today, because the use of penicillin as an oral drug has reduced significantly, excepting for applications as a skin ointment or things like that, but whenever it has to be administered orally, we always look for some derivatized penicillins, and ampicillin is a major product where 6-APA is the intermediate. Now, in such a case you see the reaction is inhibited both by P as well as A, both the product inhibit the reaction. I have just for the sake of writing the expression, I have just named as P and A, and in one case, in the case of A, it is inhibited competitively. A is a competitive inhibitor, and P is a non-competitive inhibitor. You may also sort of arrive at cases where there is substrate inhibition also. I think the life can be very, very complex in such cases, and for example, in the case in this practical case of penicillin acylase catalyzed hydrolysis of penicillin, the kinetic rate expression comes as V equal to K2 E naught upon 1 plus Km upon S, K dash M upon S, 1 plus A upon KIA. I am using the same nomenclature as has been reported in the one of the reports, and KIP, but I think that is self understandable, 1 plus K dash M upon S. The kind of and of course then they have also developed then kind of your the reactor performance equations based on that, but the quantitative comparison of CSTR and PFR in such cases will become more and more complex, but of course, before taking up the final design or analysis of the reactor system, one need to look at the reactor performance equation based on the actual reaction kinetics which is applicable, and of course, in this case I can cite you the reference. Now, this has been the case of penicillin acylase has been very detailed, in a detailed manner has been analyzed, and the reactor performance compared by Warburton and associates in Biotech Bioengineering. Volume 15, page 13, 1973. I think that is one case which illustrates the, I mean, how to use the reaction kinetics for the design of or the analyzing the reactor performance of for any given enzyme, a practical enzyme catalyzed reaction, which is not a theoretical one, but which has been used practically, and the process or the system is commercially used all over the world. So, now besides the inhibition pattern, now this the next step comes. If you recall, we have looked so far the relative concentration of substrate, feed substrate and the Km, S0 upon Km, the magnitude of S0 upon Km, the regime, kinetic regime of the reaction. We have also seen the fractional conversion and productivity. The third item we have seen is the inhibition pattern which the kinetic reaction follows, and probably another pattern which is very important in analyzing the immobilized enzyme reactors is the reactor type and operational stability. As I mentioned that, I think one of the most important motivating factor for looking at immobilized enzyme was the operational stability. That means, we can use them continuously over a very long period of time, and we must also look that how the reactor type influences the operational stability. I mean, the system which is more operationally stable has also some desirable features, even at the cost of productivity or fractional conversion, all those parameters taken separately, but operational stability will now again here also it is a very general, I mean, sort of feature that we can divide the operational stability in two major patterns. One of the major pattern is where the thermal deactivation or the loss of enzyme activity during continuous use is independent of substrate concentration. Now, obviously, if it is independent, that means irrespective of the substrate concentration in the reactor, the inactivation rate is constant, and which can be easily given by minus dE over dt is equal to kd into E, a first order decay rate constant, that is what we are familiar with. Now, in such cases the life is simple because the substrate concentration is not involved in the, so the thermal deactivation, the reactor performance can be simply considered on the basis of thermal deactivation, and if you put instead of E0 in your reactor performance equation as e to the power minus kd into T. If you replace in your reactor performance equation, idealized reactor performance equation, instead of E naught, if you just transfer it to E naught e to the power minus kd into T, where T is the operational time, I think you can get the modified reactor performance or the effect of operational stability on the reactor performance. And in such cases, you see the performance for CSTR, I mean, we are comparing the reactor performance at two different times, say from 0 time to time T. How does the enzyme, I mean the reactor performs, and in the case of CSTR, the kd into T equal to ln S0 x0 plus k dash m x0 upon 1 minus x0. Now, the whole divided by S0 xt plus k dash m xt over 1 minus xt. Now, here the x0 and xt are the fractional conversion in the case of a CSTR with at time 0 and t. That means, that at the once the steady state has been, see for example, we are considering all these reactor performance under steady state conditions. Once the steady state has been achieved at time t is equal to 0, the fractional conversion is x 0, and after the elapse of let us say time t, if the fractional conversion declines as a result of enzyme deactivation, and that is a fractional conversion is x t, and the relationship k d into t, t is the time of reactor operation here, is not minded that this t should not be confused with the space time. Space time is kept constant over the reactor operation over a period of time t, and only the fractional conversion is declining from x naught to x t, and this gives you the reactor performance or the effect of operational stability on the reactor performance in CSTR. On the other hand, in the case of PFR, the corresponding relationship is k d into t is equal to ln S0 x0 minus k dash m ln 1 minus x naught upon S0 x0 minus k dash m ln 1 minus x t. Now, in the two cases you can notice that now here also you can consider the effect of the operational stability on the reactor performance. If your reaction regime, the kinetic regime of the reaction is in the 0 order, as we noticed earlier, in that case that means the k dash m term in both the parameter, in both the expressions will be deleted. It will be only first term, and the effect of operational stability is independent of the type of reactor. The effect of operational stability will be identical in the case of two types, CSTR and PFR. If in case if we are operating our system in the 0 order regime, whereas if we are operating in the case of first order regime, the first term will get out, will be neglected, and then the difference in conversion decay rates between PFR and CSTR will be magnified. Then the conversion, the x t value in the two cases after a elapse of time t will be different in the two cases, and the output of the PFR plug flow reactor essentially will decrease much faster with time than in the case of CSTR. You can check that when you put down some arbitrary values, you can see that in the case of PFR, for a substrate independent thermal deactivation, the output, that means the fractional conversion after time t, will decrease much faster than in a CSTR. If substrate the deactivation is not linked to the substrate concentration, and therefore, in such case the CSTR will be a desirable parameter. On the other hand, if you look at the other kinetic pattern of thermal deactivation, if suppose the thermal deactivation, this is also a very common situation, because in most cases it is understood that the enzyme is more stable in the presence of its substrate. So, if higher the substrate concentration, the thermal the stability is more, its Kd value is much less in the presence of substrate, and the deactivation expression can be written as minus dE over dt equal to k dash d upon s into E, where the deactivation rate is inversely proportional to substrate concentration. Higher the substrate concentration, deactivation rate is slow. Such situation. Now, in such a situation, for a CSTR you can very easily write the reaction the reactor performance, that is your k dash d into T equal to S0 x t minus x 0 plus S0 ln x 0 upon x t plus k dash m ln k dash m plus S 0 1 minus x naught upon k dash m plus S 0 1 minus x t. Now, this is for CSTR. Now, in the case of PFR, the situation will be much more complex, because the concentration of substrate across the reactor is not constant. So, the rate of deactivation also along the length of the reactor is different, and therefore, a simple analytical solution is difficult. One has to probably get the reactor the performance of the reactor based on operational stability by a numerical solution, and the analytical solution will be difficult, but in general you will notice that in the case of substrate dependent thermal deactivation, the performance of PFR will be superior compared to a CSTR, and the PFR is a desirable sort of type of reactor, and where the effect of drop in the reactor performance as a result of enzyme deactivation will be much slower in the case of PFR for substrate dependent thermal deactivation, or in other words, in the case of substrate independent thermal deactivation, the reverse is true. The CST the PFR, the decay of the reactor performance, decay in the reactor performance will be more pronounced in the case of substrate independent thermal deactivation compared to CSTR. CSTR is much more desirable. So, basically now to summarize what we have done, as far as the idealized reactor systems are concerned, we had originally defined our idealized reactor systems, which means that the reactor systems we are considering the extreme fluid dynamic regimes, back mix and plug flow. There are no not very significant heat of reaction, isothermal operation. We have also not considered any of the mass transfer limitations or partitioning effect in the system, and under those questions, if you compare the two major types of reactor system, continuous flow reactor system CSTR and PFR, we have to analyze the reactor performance for a given reaction on the basis of the relative concentration of substrate to the Km value of the reaction. Basically it applies to basically it amounts to looking at the reaction kinetics. Then I think we need to look at the effect of fractional conversion and productivity. What is a desirable feature, whether we are looking for high fractional conversion, and that is the demand of the system, or high productivity depending on the nature of product stream. Then we had to look also the inhibition pattern, if any. Of course, in some cases if the kinetics is much more simple, one can very easily approximate it to a first order or zero order or even Michaelis-Menten, the life is simpler, but in case if there is an inhibition pattern, that must be taken into account for analyzing the reactor performance. And finally, the operational stability of the system as a result of the effect of the enzyme deactivation during continuous operation of the two different types of reactor will also be influenced by deactivation pattern. And as a matter of fact, one can not decide absolutely whether a CSTR is desirable or a PFR is desirable. Under different sets of conditions, under the requirement of the reaction system, the process requirement, one has to make a choice and compare in terms of the overall productivity or the desired parameter, whatever are the. So, I think that is the sort of system that we have to look for our ideal reactor performance. We have to analyze. Of course, now besides ideal reactor performance, we have so far not considered anything about mass transfer, non-ideal flow. This is the reactors, the practical reactor which we are talking, like we talked many of the configurations like which were combination of CSTR and ultrafiltration reactor, or a sort of a hollow fiber module. They may not be ideal flow regimes, ideal flow dynamics. They may vary somewhere in between the two, and that flow behavior also might influence the reactor performance. So, we will take those cases individually in subsequent classes.